Hello, everyone. I'm happy to be here today, and it's great to see like the big crowd that came from all over the world to learn about like machine learning for drug discovery. I think, yeah. I'm just waiting for my slides to be up. So again, to reintroduce myself again, my name is Dominique Beaini. I've been with Valence for 5 years. I'm also an adjunct professor at University of Montreal with a very small lab. You'll find my students here, so please talk to them. They're great people. So today, my talk is a bit different. I don't have any DALL-E generated image or any image in general. It's going to be a visual presentation about like a graph neural network applied to molecules. But because many people here don't know what graph neural networks or what graphs are in general, so I will start. We'll start with that aspect. So, yeah, hello everyone. So, I'd like to introduce you to Graphy. Graphy is my assistant for today, and he'll take us through the visit into the molecular graph world, learn what are graphs, look into like the standard GNN architecture that are being used, and how to build more expressive GNNs. And of course, at the end, we will build a graph transformer together and scale it to infinity and beyond. So let's first look at the anatomy of Graphy. Graphy is composed of nodes and edges. In green, you can see the nodes, and in red, you can see the edges. And they each have a different number that is assigned to to these nodes. The graph can be represented as an adjacency matrix, and this is how we represent it usually when we do machine learning. So the adjacency matrix is of size n by n, but it is a very sparse matrix where you have, and the matrix is also symmetric. So the same, everything that you'll find in the upper triangle, you also find in the lower triangle. And how the adjacency matrix is built is that for each edge, it looks at like the assigned number of the two nodes that connects them, and puts an entry in the adjacency matrix. So for example, here you have an entry in the first row and second column because first node and second node are connected. You also have the same entry in the second row and the first column. And you repeat that for every edge. If you want, if you have a double bond, you can put 2 instead of putting 1, depending on like the application that you want to do. And you continue doing that for the number of edges that you have. So in the end, what you have is a sparse matrix that has as much number of entries as there are edges. And for each of the nodes and each of the edge, you can define a vector, because we like vectors in machine learning. So this vector represents the features of the node and the atoms. And you can basically concatenate them in the same order that they are presented. And this gives you what we call like the node feature matrix and the edge feature matrix that are assigned to the graph. So these are the typical things that you'll find, for example, if you use libraries like PyTorch to do graph neural network. This is what you'll find in adjacency matrix, or sometimes it's just represented as the connectivity with the rows and columns of that matrix. You'll find the node feature matrix and the edge feature matrix, and the goal is to see how you can propagate this information between nodes and edges for your graph neural network. One thing that's really important to know is that there's permutation invariance in the graph. So here we'll focus on like node 1 and 2. So if you look at Graphy right now, you can see we can easily swap the ordering between 2 and 1, and that doesn't change anything in the representation itself, but it will change how the adjacency matrix is represented. This implies that you swap the rows and the columns in the graph. So if we look again, you swap the 1 and 2. And what it does is that this swap first row and first columns of the adjacency matrix. When designing graph neural network, it's really important to keep in mind the permutation invariance. If you don't keep that in mind, then you might destroy the information that you had at the beginning. And basically, like you can shuffle any in any order that you want. So I showed initially 1 and 2 get swapped, but you can swap any the order in any way that you like. Another thing that we like to use a lot, especially myself, is the Laplacian matrix. So how do we define this Laplacian matrix? Is first by defining the degree matrix. So for the degree matrix, you define, it's a diagonal matrix that's defined as the sum of each of the rows. And you do that for every row and you end up with your degree matrix. So the degree matrix really represents how many edges are present at each node, and it's represented as a diagonal matrix. And using the adjacency and degree matrix, you can do lots of stuff, but one of the fun stuff is to compute the Laplacian, which is simply d minus a. The Laplacian is a very important concept, and it's also present, like, for example, in images. Yeah, it's a very important mathematical context that we can find also, like, in theories of electromagnetism, for example, and what we'll discuss later, we use that to compute, for example, eigenvectors and eigenvalues of the graph. So now that we've studied what is a graph and how the graph is represented, we'll look at what is a molecule. So if there's a chemist, please close your eyes for a second. This molecule is not really like the best looking molecule, but it looks like graphene. You can find a perfect match between the two. So why is that the case? Like, I won't say molecules are defined as graphs. In the previous talks, they talked about different representations of the molecules. And yes, you can talk about the 3D structure, you can talk about the quantum mechanics, but when you go to the pharmacy and you buy a drug, you buy a graph. When you look at the patent, it's defined as the graph. And now how this graph behaves can be represented in many different ways. But this is why it's important to be able to build a good graph neural network that can really capture the information of the graph. So now let's look at the anatomy of the atoms and bonds, and how do we represent that? We talked earlier about the node feature matrix and the edge feature matrix. So these are represented like you have as many rows as there are nodes for the node features and as many rows as there are edges for the edge features. And one simple way of representing them is one-hot encoding. For example, like you have a limited number of atoms and you have a limited number of possible bonds. I think like there are roughly like around 100 atoms in the periodic table. So you can just define a 100 length one-hot vector and just puts ones and zeros, whatever, like if it's hydrogen, it's the first one, carbon would be the sixth one, and so on. For the edges, or the bonds, the chemical bonds, like you usually have like single bond, double bond, triple bond, aromatic bond, and a few other kind of stuff. So you can also define it in a small vector. But something that's really cool is also if you take inspiration from the periodic table and you then define other features like as floating point numbers like mass, row, and columns, it also helps a lot. And actually we find experimentally that including the row and the column of the periodic table helps the model generalize better. And the same thing can be done with the edges. You don't have as many features, but you can think about like the length of the bond, the chirality, whether a bond is rotatable or not. So now that we know what is a graph and how a molecule is represented, we want to focus on how to do molecular property prediction. So you typically feed your graphy into a GNN, and that GNN does predictions. So this was covered by the previous talks. But I want to specify something like usually the two things that you find is either binary classification as 0 or 1 and regression. If you have many classes, it's a bit different than like what you have in computer vision. Like you don't classify like it's either a dog or a cat or a car. It cannot be all three. But for a molecule, like usually can be all three. It can be toxic and bind to protein A and bind to protein B, and also being like, so it can have many different properties. So usually we find binary classification rather than multitask classification. And regression is also used quite a lot. So regression is like, for example, predicting the solubility or giving like a value to the activity rather than just active or inactive. But what we find the most is actually binary classification. So Now we want to talk about how do we design a GNN. We need to deal with the permutation invariance. We need to deal with the varying number of nodes in each neighborhood, but also the varying number of nodes in the graph in total. So compared again to images where each pixel has 8 neighbors, or sentences where each word has 2 neighbors, here each node has a different number of neighbors. So that's a challenge. And compared to text and images where you have a clear order, here you don't have a clear order. And we need to deal also with the lack of direction in the graph. Like I was saying, there's no left or right. Everything is defined like without direction. And the expressivity. So we'll see that this topic is important. There's a lot of papers on expressivity of graph neural networks, especially applied to molecules. So how do we deal with that usually, with this problem? So for permutation invariance, as a quick summary, I'll jump in more details later, but you can apply an MLP on each node and pass the features then on the edges. So that's what's typically done. And this allows to be permutation invariance because if you change the order, well, it also changes the order of the output. There's for the varying number of nodes, usually we have what we call aggregation. So we do, for example, min, max, or sum aggregation at each neighborhood level. And there's also pooling. So it's the same thing, but pooling is like at the entire graph level, it becomes one node. Whether aggregation doesn't transform the graph into one node, it just does at the local level. But it's 2 words to say the same thing. For the lack of the directionality, most of the literature ignores that this is a problem. And for the expressivity part, we just do weird mathematical proofs that have no applicability. Hey, what are you doing? Oh, you have a better way. Okay, I'm eager to listen to you. Join me on a microscopic adventure. I'm not, no, there's no way. I'm not jumping in the black hole. What happened? Where am I? Okay, I'm stepping on the blue node, but I don't see any neighbors, as if the connectivity was completely destroyed. But why is that? I remember the blue node had 4 neighbors. So, now I understand. I don't see my neighbors, I just see the result of the aggregation function. And this, my friends, is the reason that graph neural networks lack a lot of expressivity or are difficult to design, is that whenever you want to deal with the number of neighbors that you have, you cannot see your neighbors, you only see the result of the aggregation function. And this limits the expressivity of what you can do, unless you find very, very complex aggregation function that then limit the speed or the GPU acceleration that you can have. So let's look at that. What does mean aggregation do? You have different boxes, and each boxes get passed into the mean function. It becomes a poop color box, and then passes into an MLP. And basically, if you can imagine that the features are food, well, the mean aggregation is a poop machine that transforms any food that you put into poop. But so, like with this architecture, there are simple questions that you cannot answer, like how many neighbors do I have, and what was the color of the neighbors, and what was the food that I ate. And this is what we call oversmoothing. So if you ever hear someone say oversmoothing with a nerdy face, it's just a simple word to say everything that comes in gets out as poop. There's also the problem of oversquashing, that information cannot be sent very far in the network. So thankfully, there are other aggregation functions. So for example, the max aggregation. So the max aggregation will randomly select one color, one food to be the max and not propagate the rest. So it can be useful in some cases where you want to propagate some information like that is really important. For example, if you have one atom that is always toxic, well, propagating toxicity very fast is like, it will likely help the problem. But if you have more complex interactions, then that is not necessarily the best thing to be doing. You also have the sum aggregation. So sum aggregation just transforms everything into a bigger poop. But in theory, it's not the case. So Again, you cannot answer like necessarily what color are my neighbors. In theory, you can. I'll show you a bit how. And it also like has a low pass filter, but it's sensitive to the degree, so it's still better than the mean aggregation. But information gets distorted a lot by the degree of the nodes that you have. It's not such a problem in molecular graphs because you typically have between 1 and 4 neighbors. You never have like 20,000 neighbors, which is the case in social networks, which then would completely cause everything to explode. But it's not the case here. So mathematically, how does the sum aggregation allow you to pass the information better is that if you can imagine that the initial featurization kind of sparsifies the information in the way that is represented here, well, you can see that the sum aggregation will just reconstruct a box that is has all the faces that were previously shown. Well, this is in theory. In practice, it's another question. Other methods are like gating, where you take both nodes, like the receiving node and the sending node, and you pass that into an MLP or an attention mechanism. And that decides like of the weight that is given. So the weight can either be for all the features, or they can be also for a subset of the features, like if you have multi-head or if you have a multiplication, for example. You repeat that for all the edges, and here you can see that some of the edges becomes black, others are still there, so that the information is weighted based on that. And yeah, so this, depending on the gating and like what tricks you add, it can help like get questions like how many neighbors do I have, but it's more difficult. But it definitely helps a lot with the problems of over smoothing and over squashing. And another architecture that is usually the one that works best in molecules is called the MPNN, where both the sending node and the receiving node and the edges in between go together into an MLP, and that MLP decides of the message. So here, what's different is that the function is no longer a function of the node, becomes a function of the edges based on the two nodes that connect it. And I think like it has a lot of intuition about like how chemists would also think about a molecule, like about the connection between two nodes rather than like nodes trying to communicate together. So I think because of that inductive bias, it makes it more suitable for molecules. And in general, like it works a lot better. There's also like the possibility of like combining different aggregation functions instead of just doing mean. What if you do mean and sum and max and standard deviation to get a better idea of the population around you rather than like a single information about the population. If I am to take the average of everyone in the room here, it's not that representative of the room. So now we zoom out. We're no longer in the black hole, and we want to look at WL expressivity. Hey, you have glasses now. Nice. So WL expressivity okay, who here thinks that the two graphs here on the right are the same? Okay, perfect. I see one person. So only one person. You're the only person that's right. These two graphs are the same. Because, well, let's shrink again and zoom in again on the different nodes. And here we'll play this game. We start with these nodes that have each two neighbors, and we'll walk through the graph and see how many neighbors we have. And like, suppose these are molecules, like you can imagine all the nodes are the same or the bonds are the same. They're all carbon atoms. And you walk there, two neighbors, three neighbors, two neighbors, two neighbors, three neighbors, 2, 3, 3, 2. Perfect. We have the same list of numbers. So here, my friends, is the proof that they're the same. Okay, yeah, maybe they're not. There's something that's missing from that, is that when we have a view from inside of the graph, we're missing a lot of information. And this is, again, a visual way of like talking about the WL expressivity, or like Weisfeiler-Lemon expressivity, which is a mathematical concept that can be a bit harder to grasp, but here you see like the effect on graph neural network. And there are things that you cannot see from inside the neural network without having a positioning system or an ordering system. But we said before that we cannot have an ordering of the nodes. So yeah, graphs have no direction. But if you look again, and you really think about that, well, you can actually find directions and you can actually find positions in a graph. If you look at Graphy here is, you can see that Graphy is taller than he is wide. You can define kind of two main axes. So let's do that. You have the height and the width, okay? And this is not random. This is based on like how you see the graph. And how can you find that mathematically? Well, there's this concept, like we talked about the Laplacian matrix before, which is the degree matrix minus the adjacency matrix. And if you were to take the eigenvectors of that matrix, well, it will give you like the longest length and the second longest length representation and the position for each node. So the one thing is that you can randomly flip the sign of these eigenvectors. Like there's no way of saying like which is up and which is down, but you can say this is the longest length, this is the second longest length. And if you were to color the graphs here by the longest length, by a position of the longest length and second longest length, using the Laplacian eigenvectors, this is what you get. And now you have enough information to distinguish these two graphs. Like, for example, on the right, you have 3 nodes that are green, and on the bottom, you have only 2 nodes that are green. And this increase the expressivity. So the simple way of doing that is let's concatenate that to the node features. Not just take one hot encoding and periodic table, but also take position. And another way, though, is also to use that to bias the weights by which the message gets passed into the neural network. I will not go into details with that, but like you can really imagine how this can be used to bias the attention or to bias the message passing that happens. And this allows to be more expressive. So if you were to use a graph neural network without positional encoding or structural encoding that I will define later, I give you these 2 molecules and your graph neural network will tell you the same. And then you make your prediction, you send it to the chemist, and the chemist is just like, no, they're not the same. So never forget to do that. What are structural encoding? It's another way that is also very powerful in molecules, because molecules is really about structure, and chemists have been analyzing the structures of molecules for a very long time. So again, this is a good inductive bias. You can just imagine like, okay, identifying squares and triangles, or pentagons and hexagons that you find a lot in molecules. But another way is also to do random walks. So doing random walk is kind of like you start at a node and you look at the probability of going back to that node after a certain number of steps. We can see in the squares above that if you were to do a random walk of 3 steps, you would never land back on your own node because of the square structure. But on the bottom one, because of the triangle structure, there's a significant probability of landing back again on the same node with 3 steps. So it's another way to distinguish between squares and triangles. And you can do that with any number of steps. So for 4 steps, the probability distribution changes. And now we can again we can again be more expressive, and we can again use that to bias how message passing is done. Like there's a lot of papers showing that well, let's always pass the message between all nodes that are within the same hexagon, have a different message passing, and that allows like a better form of expressivity that is also a good inductive bias to how chemists think about the molecules. Or you can also concatenate that to the network, and the network will learn, hopefully. Now let's talk about biased Fourier attention. So, well, attention is all you need. So never mind graph neural networks. We can just put a transformer there. Oh, wait, maybe I was wrong. Graph is now fully connected. There's no more structure. But we should have read the fine prints. Attention is not all you need. You also need good positional and structural encoding. you need a biased attention, you need a task that depends on long-range dependency, and you need lots and lots of data, and much more. Okay, so attention is not all you need. Sorry, I was mistaken. Yeah, what is biased attention? It's another way of making attention more specific to graph neural networks. So this is the typical structure of like how an attention layer is based. You have the query, the keys, and the values, and they go into matrix multiplication to define query and keys go into matrix multiplication to define the weight by which the value gets propagated. And here it's simply like you can have another function on the edges that you then either sum or multiply with the weights from the atoms. And this means that like it's not just, okay, well, if I have a carbon and an oxygen, pass the information, but you can pass different information whether you have a single bond or a double bond between that carbon and that oxygen. And it changes the things. And you can even bias the attention to treat real connectivity, like covalent bonds, differently than like non-covalent bond between, and that will allow the attention to have more bias towards the actual structure of the graph, rather than just try to learn everything from scratch from the positional and structural encoding that you give it. So thank you, bias. Graphic can now retrieve its own structure. Yeah, now we talked about like needing lots and lots of data for transformers. So what if we use pre-training to get that data? When doing pre-training, we can think about like all the biological assays that exist, like cell assays, transcriptomics, the chemistry assays like protein assay or physicochemical solubility, for example. We can think about quantum mechanics simulation, for example, to get homolumo gap or partial charges. And we can think also about doing self-supervised learning. I'm not really a big fan of self-supervised learning for graphs because it really doesn't allow us to capture anything else than the structure of the graph itself. Like you can think, for example, self-supervised learning, when you do that on images, for example, like you learn that an image is rotation invariant, is noise invariant, is zoom invariant, and all of these things, when you start to learn them, well, you start to understand like what is an object, what should I look at, what are the features, and like naturally classify the different images without even having labels. And the same with text. By just learning to find the missing words, you inherently learn the definition of words and the context in which words are put. So with self-supervision on graphs, like you don't really learn anything about the physics, the biology, and the chemistry, which are really the thing that drive the chemistry. It doesn't mean that it's not useful. It can be used for pre-training, for example, like to get your graph neural network to first understand the structure, but then you need a way to have it understand biology, chemistry, and physics if you really want that to work. So one thing that my team and collaborators worked on like during the past year is releasing the Graphium data sets. So by far the largest data sets of supervised label for molecules. I'll talk a bit more about that. And the Graphium library that allows to do multi-level multitasking, multi-level positional encoding, and multi-level graph transformers. I'll talk again more about that. So let's talk about the data sets, for example, that we included in the large mix data set. So these include cell assays from transcriptomics L1000, where we have about 15,000 molecules in the data set and roughly 1,000 labels. And the labels are either like 1 as having positive effect, 0 no effect, and -1 as negative effect. Then we also have like the PCBA 1328 dataset, which regroups public assays from 1,300 different assays from PubChem and puts them in a single matrix of like 1.6 million molecules. This matrix is very sparse, so like roughly 95% of the data is missing. Then we have the quantum mechanics data, which comes from quantum mechanics simulation using density functional theory. And for that, we have more dense matrices. So roughly 4 million molecules. And we got, sorry. Yeah. Anyway, so we also have like some node level features. So compared to most of the data set that you find for molecules, which is just the property of the molecule in itself, we also have like the charge at each individual atom. So this gives you like additional information. Yeah, so I went through this slide. So now let's look at multi-level multitasking. So you take your graph and you put it into a part of the network to pre-process the graph. Then you go into the GNN layers that we discussed before. You have then pooling, a shared MLP, and then different MLPs for each of the tasks that you have. And this is the typical structure that we want to do when doing multitasking. So the shared representation allows like really the neural network to learn things that are correlated between physics, chemistry, and biology. But you also have like another separate MLP for the node level tasks. And again, you can have many different task heads. And of course, you can also have like edge level and node pair level, but we didn't include that in our current data set. Now let's, yeah. So let's look a bit at what was before the GNN. So before the GNN, we want to featureize the molecule. So we pass that into like what we call the encoder manager, which allows to put information like distance between nodes, random walk, eigenvector, eigenvalues, pseudo inverse, and even things like chemical property from the periodic table. And these get mapped then to whether these are node pair, graph feature, add feature, or node feature. But we also define like this fuser in the Graphium library that allows us to project any of the information at any of the different levels and then pass that all into the GNN. So this is a powerful GNN that is able to take into account the positional encodings that we discussed before, but also the periodic table. And it's composed of two different blocks, message passing and transformer, although we can select whether we want only one of these. And we can see how the edge information, node information, and node pair information is passed in all of these. So the message passing and transformer gets concatenated together, fed into an MLP. And that MLP also get a graph level representation that is again fed at the node level. So we don't want, one thing that's important is that we don't want the information, sorry. Yeah, we don't want to just do message passing and then like all the nodes have no idea about the global structure of the graph. By doing a pooling at every layer, sometimes it's called virtual node, or you can just call it pooling. It allows the network to always know the global structure at the same time that it's learning, and this allows like to learn a more meaningful representation. So if we go back, so we had graphy goes into the encoder manager, goes into the GNN, and we had all these layers. Now we want to do fine tuning. So when we do fine tuning, we can drop the parts that we don't want. And then once we drop these parts, we can take any of the MLP that we want and fine tune that on a new task, as you can see in the top left, in the top right here. One thing that's also possible is to freeze the different layers that you don't want to fine tune. And in general, like this works very well. And it's often what we call like a machine learning fingerprint. So the two talks before talked about like how ECFP can be used as a very strong baseline. And this is an alternative. What if the fingerprint that you have is learned by a machine learning algorithm rather than being like just based on structures? And once we do fine tuning, well, the next question is, can we scale that? Can we scale the model? Can we scale the fingerprint such that it gives a meaningful representation when we do fine tuning? And this is the big question for the graph machine learning community that like for many years, the number of parameters in graph neural network was like below 1 million. And even like on the large scale challenge that was proposed by OGB, it never went more to than 20 million. And instead they used ensembles of like 80 different models to improve the performance rather than scaling one model. And that's because a lot of overfitting happened. Data is either small or sparse or noisy and all of that. But if you do the training the way that we showed, where you train on thousands of different assays at the same time, well, you can actually do some scaling. So these are results that we had, where like on the x-axis, it's the log of the number of parameters. And on the y-axis, we have like the normalized performance on the TDC benchmark. So the TDC benchmark agglomerates like more than 30, or I think 40 different machine learning models to do property prediction. And what you have here with the normalization is that the average performance on TDC is 0 because it's normalized. The best baseline that was implemented by the author himself, so the author ran 10 different baselines, and it scores at about roughly 0.6 as the average. And the all-time record best, so on each data set, if you take the best model, it's the line that you see here. And when we scale our model with the Graphium library, the model that we call MolGPS, what we find is that we're actually able to perform at a 1 billion parameter regime. We're actually able to perform consistently on each of the 22 data sets that we tried, consistently as the best model or close second or third among a list of like 40 different models. Yeah, so there are still limitations in fine-tuning. So we cannot continue to do that and go to 100 billion parameters and expect the trend to continue. And the limitation is that even if the model perfectly understands the entire universe, like understand all the physics, chemistry, and biology that you want, then you take a crappy data set of like 1,000 molecules that is mislabeled because like of experimental noise, and is really represent a really small part of the chemical space, your model will overfit, even if it understands the entire universe, because you're not giving it context. You're just giving it a bunch of ones and zeros that are noisy and small. So it doesn't necessarily know how to fine tune. So what if you could encode the task, for example, by giving the context of the cell on which you do the experiment, by giving the protein sequence, or by using natural language to define the task. So you can use natural language to say, this is a task of solubility at this temperature, and I want to know the property. And then the model can, like, if it's trained on this kind of thing, well, can know how it should fine-tune its representation to that task. And in that specific case, you can imagine that a perfect model would perform almost perfectly, considering like the noise that still exists in the data, but a perfect model would be able to really perform much better because it has a context of the task. And basically, like, this brings us to the question of multimodality. How do you include these things as how do you include these other modalities to help improve the GNN? And one of the big things that we decided to work on, like at valence and recursion, is to use phenomics, because phenomics is a very rich and a very important data set for recursion, but it's also very rich in the sense that, like, it takes images of the cells that contain a lot of different information that is kind of equivalent of running hundreds of experiments at the same time, but it measures them all at once. So we can have actually big data sets in these cases. And yes, they're still a lot smaller than what we see, for example, how DALI was trained. But still, what we find is that if you have a foundational model of chemistry and also a foundational model of like phenomic images, what you can do is build the DALI of molecules. And this really allows to understand like the effect of molecules on cells. So you can really imagine how, like, with that kind of model, given any molecule, you can replicate the microscopy experiment, but in silico. Or given any microscopy outcome that you desire, you can find back the molecule that generated that. And this is why I like to call this the DALI of molecules, because it embeds them to the same space, and you can plug then generative models. Paper about this model will be coming soon, so stay tuned. And yeah, finally, Don will stop talking. But if you're not tired of hearing me talking, follow me on Twitter. And like a lot of the work that was done here was done with various collaborators from very different groups. So I'd like to thank all of them from Valence, from University of Montreal, Cambridge, Oxford, and many, many other groups. Thanks a lot, everyone, for listening.
If you have a question, please raise your hand. I'll bring the mic to you.
Hi, thank you so much for your talk. It was really wonderful to hear. And I wanted to ask, when you're doing training on a ton of different data, as you showed, how do you make sure that the benchmark you choose is a robust evaluation of what you might want to do? Like you see, I think with the therapeutic data commons, it's particular tasks that it's working for, and then like what you train on is other different tasks, and generalizing that into the future. I guess your take on that, please.
Yeah, there's many different takes on that, but if I was a representative of OpenAI, I would say if you train on everything that ever exists, then you don't need to care about out of distribution, right? So that's a bit the goal. So the more and more assets that you add, then the more it learns a global representation of everything. The issue that you might face by doing that is that then like your model is never the best it could ever be on the task that you fine tune, but it is almost the best everywhere. So this is where like I think in context learning or multimodality will help, where you can instead like learn what is the meaning of the assay that you're doing, and that will help you generalize better, like be the best that you can on what you've seen, but also generalize better to things that are unseen, because in the end like there's a limited number of experiments that one can do in the lab, of cheap experiments that can generate enough data, right, that one can do in the lab. So learning with as much as possible and encoding as much context as possible is key to help make that work. Does that answer the question correctly? Cool.
Hi, so my concern in my research field a lot of times is explainability, and using transformers sometimes, at least I am pretty much overwhelmed because we lose out a little bit on the structure aspect when we look at the global information. And sometimes like there are research going on that criticize using attention weights as explainable parameters because they are focused on what information to copy rather than what information is relevant to the target. And so my question is, this might be a little far-fetched, but how can we make graph transformers more meaningful in terms of what they learn?
Yeah, so that's a very interesting question about like how to make transformer learn more meaningful things and be more interpretable and explainable. I'm not like the big expert on explainability, but yeah, one of the things that I do a lot is to use hybrid architecture first, like plug in both MPNN and transformer. The transformer will have a bit more global view and the MPNN a more local view. It doesn't help on the explainability, but if you don't trust transformer, it helps a bit on the trust on that side. Now on the explainability of transformer and on the attention weights, there's been some work in the literature, for example, of image, like for VITs, for example, where they show that the explainability of attention weight is very bad unless you add like some fake tokens at the beginning or the end of the image, where all the reasoning task that is not really needed, that does not necessarily need to go on a node, is going to be done there, and it will increase like the explainability of the other attention weights that actually happen on real atoms or real pixel of the image. That has shown like massive improvement in explainability of VITs. I haven't tried that specifically for molecules. Another thing, as I've explained, is also like adding the attention bias, like biasing the attention by whether a bond is actually there or not, and biasing the attention by the type of bond that is present between two atoms. I think it's a very critical part in making transformer generalize well for molecules. I don't know if that answers fully the question. You can follow up if you have something else to add.
One last question before we end. No? Cool. So with that, let's break for the for lunch. We'll be back at 2 p.m. here as well. If you have any question for the speaker, much of them I run all day, so catch them up. Thank you. See you soon.